So this lesson was kind of a last-minute addition, but I'll show you how it still goes with what we've been doing recently. A sequence is like a group of numbers. It's a set of numbers. If that group of numbers is described as being arithmetic, it's because they have a common difference. What does the word difference mean in math? It normally means subtract. Yeah, it normally means subtract, but since subtracting is the same as adding a negative, we can use it to describe addition as well. Okay, so let me give you a group of numbers like, oh, I don't know, 5, 10, 15, 20, 25, 30, 35, 40, 45, 50, 55, 60, right? I just read out a bunch of numbers. That set of numbers I could say is arithmetic because those numbers had a common difference. Every time to get from one number to the next, I added the same amount. I added 6.
Only 5.
Yeah, I added 5 each time. So those numbers belong to an arithmetic sequence. Okay. I'll try not to spend too much time on these first 2 pages because I'm going to lose your attention. It's going to be very abstract and full of variables and you're not going to know what they mean. So I'll just try to hit on the key parts and then get to the examples. I've had now 3 Algebra 1 classes so far today, and 3 Algebra 1 classes, at least I feel, kind of left here feeling like they understood what we were doing. So, but most of those classes had the laptops closed while I was speaking. So, so that set of numbers, or any set of numbers really for that matter, can be expressed either explicitly or recursively. The word definition that you see, sometimes they use the word rule instead, an explicit rule or recursive rule. It's just a commonality, like a relationship that the numbers share. Okay. The one that is used most frequently would be the explicit definition. This is also the reason why it's covered now. You might look at this on the surface and say, what the heck does this have to do? I could have sworn we just finished graphing. Well, what are we doing now? Well, what did you graph? We just graphed points. Okay, we graphed equations. We also graphed inequalities. And what did both the equations and inequalities have in common? They both had an adjective. They both had an adjective that was used to describe them. Linear, good. So the explicit definition, just this one, the explicit definition of an arithmetic sequence is said to also be linear. What was the most common form of a linear equation that we studied? What was the most common form? Nah, ew. Standard form is yucky. Slope-intercept form. Okay, slope-intercept. So I will show you some of the concepts from slope-intercept and how they apply here. I'll show you the parallels. Okay. What's the good thing? Another good thing about an explicit definition, I can describe everything in one equation, and I can substitute into an explicit definition. Meaning, I just started reading a bunch of numbers to you, right? 5, 10, 15, 20, 25, 30. Let's say Lydia says, hey, you know what, Mr. Romero? If you were to keep on counting, what would be the 5,342nd number you would say? Well, instead of having to count 5,342 whatever numbers, keep on counting 5, 10, 15, 20, you can plug whatever position you're looking for into an explicit definition, and it'll tell you what number falls in that slot. Okay, now a recursive definition gets basically an explicit definition and breaks it into two. And really, like, yeah, you're gonna see an equal sign, but don't even think of it as an equation. You're not gonna simplify this. I almost try to think of it as like a different language. Okay, just think of it as a format or like an arrangement, and you just have to know where to place certain things. Okay, a recursive definition describes what those numbers have in common, but it uses the number before. It uses the number that came before in order. The recursive definition isn't used as often because you cannot substitute into it. You cannot simplify it. And really the only thing it's good for, if you were to use it for anything, would be to find some numbers that are in close proximity. Like if I were to say, hey, 5, 10, 15, 20. Hey, what are the next three numbers that come? Because I'm looking for like the next three numbers, not the 5,000th number. Yeah, a recursive definition would do. You can also find that explicitly, but a recursive is basically finding things manually. Just counting one by one by one by one by one. What do they look like? Well, the explicit definition for an arithmetic sequence, there's one of two ways of writing it. The most common way is that one there. I know that might seem like gibberish for you, but just so that you know, look, watch. This is going to be just the name of the rule. F of n is a very common one, but call it whatever. What does f of 1 stand for? Look at the little key that I gave you. When you see this f of 1, what does that stand for? Yeah, the initial amount. But depending on how it's written, you know, this is a less commonly used form. This is really like the only time I've really seen it where you use this type of form is like in a word problem. I'll give you like a brief example in a second. But if you see something in the difference between the two is the parentheses. Here you see a parentheses and here you don't. If you get this form and simplify it, then it would look like the one on the left. But then this f of 0 would be considered to be the initial amount. What does the D stand for? We see that both of these have a D. What does that stand for? Yeah, that stands for the common difference. When I ask you what are the two things you need in order to write an explicit definition, or for that matter, a recursive definition, those are the two things. You need the initial amount, you need the common difference. You have to know that. When I asked you what do you need for slope-intercept form, you told me slope and y-intercept. When I asked you what do you need for point-slope form, you need the slope and a point. What do you need for any type of definition? You need the initial amount, you need the common difference. And in order to be able to define an arithmetic sequence. The n, you're not going to do anything with the n until you actually want to find the number. If you want to find that 5,000th number, then I would do something with the n. But I just put this here so that you know that the n stands for the number of the term. Where are we in the sequence? Are we talking about the first number, the second number, the third number, so on and so forth? I kind of debated internally whether to even show you these two or not. Because really, the one we're going to use the most is on the right. But just in case, so that you know that I already gave you one difference, that the one on the left over here is just kind of the one on the right, but in simplest form. But as far as when to use each one, in a word problem, let's say like, Alan is saving money to buy a fancy new record player. And he's going to save money by mowing lawns. And he makes $40 a week mowing lawns. Okay, well, what is the amount of money that he makes dependent on? How many what? How many weeks? Yeah, because we said weeks, $40 a week. I guess I could have done it based on the amount of yards, but I said weeks, so let's just go with weeks, right? So if the sequence, if when I start counting dollars, it's after I've already started counting weeks, week 1, week 2, after the week is over, this is kind of the formula to use for an after scenario. And we see the word after in a word problem. But then sometimes on a word problem, you'll see, well, hey, Alan already has $37 in his piggy bank. And then he makes $40 a week. Well, because that $37 was there before we started counting any weeks, then, this one could be called for. Where now that initial amount would be the 37. I know this seems confusing, but just try to hold your attention for 5 more minutes. A recursive definition doesn't have as many uses, and just like before, we're going to use the one on the right most often. We still need to know the initial amount. We need to know the common difference, but it's just a way of writing it. Think of this little portion of it here as being standard. You're always going to write that. Think of it like if I was translating Spanish to you. Okay? This notation doesn't mean anything numerically. It's just a way of saying, hey, f of n means any number. It could be any number. Equals means is. So this is any number. Any number is. This f at -1 means the number that came before it. Recursive definitions are based on the previous number. So that's just another way of saying the previous number. But what do you see that's common with explicit? Common difference and the original number. That word and sometimes will be there, sometimes it won't. You're just getting the two different things that you need from an arithmetic sequence, and you're breaking it up into 2 parts. Sadie, I know you look worried now, but just trust me, it's not going to be that bad. Watch, let's get to the examples. Here is a set of numbers. Most of the time you'll see it like with a comma and a dot, dot, dot. Feel free to add that. But I guess I just forgot to write it. What this is saying is that I'm starting off counting on the number -7. And I'm going to keep on counting in this pattern up to I don't know how long. And this is a yes or no question. We want to know, is this sequence of numbers arithmetic? Well, in order to determine that, we have to see if there's a common difference. A lot of times you can do this mentally. No. If you can't do it mentally and you require the use of a calculator, right, get the number that's on the right and subtract the number that came right before it. What is -3 minus -7? It's +4. What is 1 minus -3? Also +4. Or you can think of it as I go from left to right, what am I adding or subtracting? Well, it looks like I'm adding 4. 1 plus 4 is 5. So is this difference common? Yes, it is. But instead of having to do extra examples and run the risk of not finishing, let's just take advantage of this example. Even though we're not being asked to do it, let's take advantage and let's define this sequence explicitly and let's define it recursively. Let's write an equation. Let's write a function rule. And then this is like 2 different formats, 2 different ways of writing it. Okay? The first one, explicit. Let's give this a name. Let's just call it f of n. That's a very common one. Sometimes if you do Khan Academy, they'll call it a of b, but just a name. The first thing you see is just the name of the definition. That is equal to what comes next? What comes right after the f of n? If you look at the notes. No, not the common difference. That's a good guess. The initial amount, what's the first number you see in that sequence? -7, so you write that first. What comes next? The common difference. Next thing comes is the common difference. What's the common difference here? It is +4. So I'm going to write +4. And then this n minus 1 just starts off as standard. Like you just leave it there. What I have just used is I've used this formula to be able to describe what all of these numbers have in common. In most instances, if you stop here, that would be enough. That would satisfy it. It depends on the way the question is worded, but more often than not, if you leave it like this, you're fine. You have defined this sequence explicitly. But one of the nice things about explicit definitions, at least for, well, actually not for all of them, for all explicit definitions, is that they can be simplified. If possible, you can at least try to simplify. And this can be, I have a parenthesis here that I can remove. How would I remove this parenthesis? I would distribute -7 plus 4n minus 4. 4n minus 11. Remember I told you that there's a word that can be used to describe the explicit definition of an arithmetic sequence. What was that word? There is a word that can be used to describe the explicit definition of a arithmetic sequence. Linear. This formula here has linear principles in it. What are those linear principles? Slope and y-intercept. If I were to ask you what's the slope here, what would you say? 4. The 4 is in front of the n. Hey, geez, look at what else that 4 happens to be. Common difference. You have my permission to make that association. That is a perfectly fine association to make. Common difference is the same as slope. If I were to ask you what's the y-intercept? -11. Now you don't see a -11 anywhere here on the page, but what that -11 stands for, I know that this is all, is yeah, like now that I remove the parentheses, if I didn't have the parentheses, that would be that f at 0. Remember also y-intercept is what happens when x is 0, so now it's what happens when n is 0. If I put in a 0, watch, even let's go here. Look at what happens if I put a 0 in for n up here at the top. 0 minus 1 is -1. -1 times 4 is -4. What's -7 plus -4? No, -7 minus 4? -11. A more visual way of thinking of it, we consider this to be our first number, right? That was the first number you saw, the -7. Well, if there was a 0 number, that would have come before. If we were to go backwards and instead of adding 4, we were to take away 4, what number would have been before that -7? -11. So this shares the same principles as the linear functions we saw before. Frank, should I take a picture and send mom? Yes, Mary.
So when you're setting up the equation, n minus -1.
The n minus 1 part is just part of the formula. I only use that. Okay, so now like what? Let's go back here, right? And let's say Mary got out of practice today and she's like still thinking about it. She's like, you know what? I really like this sequence. I want to keep on going. I want to know what the 532nd number would be if I were to start at -7 and add 4, and like let's get one my calculator. +4 equals, +4 equals, +4 equals, +4 equals. What would my calculator say after I've hit equal for the 532nd time? Well, I don't. Maybe like your fingers will get tired hitting +4 equals, +4 equals. So the easy way would just be to get that 532. That's the number you wanted to find, that position, and plug it in for n. When you do that times 4 minus 11, that would give you what number shows up there. Yeah, these are functions. This is function notation. Let's go by numbers that you see here. What is the third number that you see? Because there you can see it. That's not often distance you actually see it. 1, right? Let's plug in a 3 for n. 4 times 3 is 12. 12 minus 11 is 1. Every single number that falls in the sequence would have to abide by this rule. Okay. Now let's get this rule and just change it to a different language. Let's just write it a different way. Not as useful of a way, but it's just another way, and that's recursive. What we do with recursive is like we break this up into 2. Sometimes that word and is written, sometimes it's not. Okay, what you would do is separately just write, okay, what's my first number? -7, so you would write that first. You don't do anything there, you don't solve anything there, you don't substitute anything there. You're just saying the first number is -7. And then there's that common terminology. F of n is equal to f at n minus 1. And then what's the common difference? +4. You don't distribute there, you don't remove the parentheses, you don't solve for n. It's just a way of writing it. So that if they gave you a sequence in any of these forms, you would know where to find the common difference and the initial amount. You just got to know where to locate them. Let's do another one. Is this arithmetic? Well, let's see. What's the first difference here?
3.
+3. How about the next one?
6.
+6. The next one?
12.
Is this difference common? No. Because this is not common, that just means it's not arithmetic. Does that mean that you can't define it explicitly and recursively? No, it can be done, but you're not responsible for that. The only thing you have to know is how to define an arithmetic sequence explicitly and recursively. Yes. All of these have a pattern. The fact that it's a sequence is what makes it a pattern. What makes it arithmetic is that that pattern is specifically one that is linear. That linear means that you're adding every time. You're adding the same number every time, or you're subtracting the same number every time. That's what linear means. That's what arithmetic means. Okay. There's several types of sequences, but in Algebra 1 we learned 2. One of them is arithmetic. The other one is geometric. Geometrics don't have a common difference, they have a common ratio. That's geometric. Geometric is multiplying. But you're not going to learn that now.
Could you be adding and subtracting?
Adding and subtracting?
Like at the same time, like say you like add 4, then subtract.
Oh, but then it would be common. Now you're changing it every time. You can make a pattern out of that. You can make a sequence, but you wouldn't be able to define it arithmetically. Remember, common means the same.
Wait, so if it's not arithmetic, then you don't do anything?
Correct, because all you're responsible for here is knowing how to define arithmetic sequences. Yes. All right, so here we're going to find the sequence. What I mean by find the sequence is let's write this both explicitly and recursively, and then let's find the next two terms. What's the difference between the first two? -6, then after that? -6 after that? If you're not sure, take the one on the right and subtract the one that came before it on that. I'm not being asked if this is arithmetic. I'm already assuming that it was. I just confirmed it. So now, Frank, let's define this explicitly and recursively on. Yeah, I'll do that at the end. I'm still finding the. When I say find the sequence, I'm talking about let's actually define it. So explicit, let's just call this f of n again, but you can really call it anything. You'll see it called several things. C and T, A and B. What comes after the equal sign on the explicit definition? The initial amount, good, which in this case is 10. What comes after that? The common difference is -6, and the parentheses stays as n minus 1. You have now defined this explicitly. Most of the time, this is enough. But I like to show off, so I'm going to distribute. I'm going to simplify. So I can also write this as -6n plus 16. Same thing. One is not any different than the other. I can substitute here if I want to. I can substitute here if I want to. But either one is fine. If all you're being asked to do is define it, either one is fine. Well, what do you mean by get the answer? When you say get the what answer? What are you being asked to do? Okay. Now let's do the same thing. Yeah. 10, and every number that came before it minus 6. It's just a different way of writing it. Normally, when I'm going to find a missing term, usually the most convenient method is the explicit one. But because these numbers are coming like right afterwards, I would even tell you just to use the recursive one, because the recursive is based on the number. Like, if you think of this as being a language and you know how to read the language, like I could get these numbers and erase them. And you would know by reading this recursive definition that it says, hey, Jordan, start at 10, and then every number after 10 will be the number that came before it minus 6. So, yeah, now if I put those numbers back off, I can just keep on and say minus 6, minus 6. What's negative 8 minus 6? It's a negative 14. What's a negative 14 minus 6? Negative 20. Now, Jordan, look, you think you were just saying before, how would you write that? Well, I gave you 4 numbers, so where in the sequence did that negative 14 fall? It was the 5th number, so you would write f, which is the name of the function of the sequence. F of 5 is equal to negative 14, and f at 6 is equal to negative 20. Those were the next 2 terms. To show you, though, that explicit would have still worked, pick one of these, Jordan. Okay, so let's get that 6 and plug it in up here for n. What's negative 6 times 6? Negative 36 plus 16? Negative 20. The same thing I got. So if I get either of these, I didn't need to because there were, if I would have asked you, hey, Jordan, what's the 100th number in that sequence? Yeah, I would have just used this one because I'm not going to, if I'm going to use recursive, then I'd have to find the 5th number, the 6th number, the 7th number, the 8th number. I have to go one by one. But since I just needed the next 2, it still works. If I get these and plug them in for n, when I'm done, I'm going to get those numbers there. Mm-hmm. Right, Frank? So here, for this next one, scratch off what's on your paper because, I don't know, I think I changed the directions around, but I didn't change the numbers around. So we're going to do the exact same thing, but let's change the numbers to the last 2 numbers to 20 and to 29. And then I want you to do the same thing. I want you to find the sequence and then find the next 2 terms. Okay, so I gave you a head start, so I'll come up behind you. Plus 9, plus 9, plus 9. You should realize that's the common difference. So the explicit definition would be that f of n is equal to the first number, which was 2. Then the common difference was 9. And then yes, it is n minus 1. That's if you want to simplify, you don't have to necessarily do this, but I like to. You get 9n minus 7. But in order to write, like once you have this written, you have already satisfied the explicit definition. It's just, I like to write it in simpler form. Recursively, I would just say f at 1 was 2, and then every every number is the number that came before it plus 9. I don't substitute in there. I don't remove the parentheses. I don't distribute. I don't do anything with it. It's just a different way of writing it. Which in this case is probably the more handy thing because, yeah, what this tells me, what in that language, what it's telling me to do is if I wanted to find anything else, like find these next two, I would just do plus 9 and plus 9 to the one that came before it, which would give me 38 and 47. So the way I would state that is that f at 5 is 38 and f at 6 is 47. But just to show you that the explicit still works, Mary, 9 times 5 is?
What?
9 times 5 is?
What?
It's okay, it's not a trick question.
I'm sorry,
9 times 5, that they show you, you get your hand, you go 1, 2, 3, 4, 5, and then it's like 4, 45. 45 minus 7 is? It's dua. No, yeah, it's 38. So I just want to show you that it still works. The only reason why I use the recursive, like why I found these manually or digitally, if you want to say that, is because I was only being asked for the last two. But now look, if you look at the next two examples, now they're giving me the definition. I'm not being asked to write it. Let's identify what type of definition is this. This is explicit because everything is being given to me in one equation. This is a rule that everything would abide by. So let's find the second, the fourth, and the 11th. Better yet, let's even do this. Because this one we're going to do together. If you want to do it on your own, that's fine, but let's do this together. Let's say look, I'm not being asked, but let's say I was being asked, what's the first term? I can't see the numbers. What's the first term in that sequence? 5, yeah, because you know where to find it. Sure. Okay. What's the common difference here? -3, sure. Okay, so nobody says you have to simplify, but I like to simplify. Be careful with the signs. You should end up getting -3 and plus 8. So now we change the name, and they changed the name. Now this is not being called Frankie, now it's being called Alex. So Alex at 2 is -3 times 2 plus 8 is -6 plus 8, which is 2. If I were to write the numbers out, what would be the second number I see? You just told me the first number would be 5. What would the second number be? It would be 2. Okay. What would be the fourth number that I see? -12 plus 8 is -4. Good. And then what would be the 11th number that I see? -3 times 11 plus 8 is -33 plus 8 is -25.
What?
I think it's because you had your hand down. Huh? What?
I mean, technically, couldn't you just like not use the equation?
Yeah.
Subtracting.
Okay. Here you go. Alan and Alan only. Find me, go ahead and do it one at a time and let me know when you're done, okay? Okay. For everybody else, you can do this one. This is the last example. I want you to find the second, fourth, and 11th term. Raise your hand when you have it. Lydia, you got it already? Okay, what'd you get for the second one? You guys jump ahead. Go, Lydia. For the second term? For this last example here, the second term you got was 8? No? Okay, well, what'd you get? Diego, what'd you get? Oh, you're joking. Just raise your hand when you have all three. I want all three. On this last example, that's I'm sorry for my handwriting. That's a 5. That's not an S. That's a 5. I've been told my S's look like 5s and vice versa. You finished everything, true? You got it all? I want all of them. Don't just shout. You finish all three, and then you raise your hand, and then I call on you, and then you give it to me. Andy, what you got? You have all three? What'd you get, Andy? What's the second number? What's the fourth number? Okay, and what's the 11th number? Okay. Mm-hmm. Yeah, of course I am. I'm just giving you guys.
I got the answer to your equation.
Wait, I didn't know you were gonna try me to stay awake. Did you try to simplify, Lydia? So A at 2. Now, look, I want to just be clear on this. I could substitute up here if I want. I could put the 2 in for the n of third. It would still work. It's more just a preference. I like to simplify. Simplifying doesn't scare me. So 5 times 2 minus 8, that is 2. The second number will be 2. He slept all class and you just gave away, you took my Skittles just to give them away? You're going to make me want to stop sharing.
I didn't hear equation.
The fourth number was 12. And then, yes, 55 minus 8 is 47. Any questions? All right, so at least we finished. Should have finished a little sooner, but we got 10 minutes left.